introduce Professor Salomon, who will be talking about the Mercury source and saprolites in the Suriname gold-rich greenstone belt. So Professor Dr. Salomon Kroonenberg is an endorsed professor of geology at the Anton de Kom University of Suriname, with a PhD from the University of Amsterdam on geology on the southwestern Suriname. Professor Kroonenberg has decades of international experience in geology, physical geography, and remote sensing. He has held professor roles at Wageningen University and Delft University of Technology, and is an honorary professor at the Moscow State University. His research focuses on Suriname's geology and history, Suriname geological history, alongside prior work on sea level changes in the Caspian Sea. Professor Kroonenberg is the author of over 170 scientific publications and 8 books, including the award-winning The Human Dimension, The Earth in 10,000 Years. So give a round of applause for Salomon.
Thank you very much, Thijs. So much words just for one man. I am a physical geographer by training from Amsterdam, as Thijs said. And I have had geological jobs, but I have also jobs in physical geography and in soil science. I have been professor of geology here at Wageningen University between 82 and 96. A few people in the audience still remember me from that time and so. But I have always been a bit on both geology and soil science. And recently, since the last 8 years, I am working at the University of Suriname, Anton de Kom University, and that's pure geology and so. And we don't look so much normally to soil processes because our main time slot actually is between 2.1 and 1.9 billion years. It is the geological history of Suriname. So this is actually something, a little bit a side path from the work we do there. It is about Mercury. Of course, I don't have to tell you about the problems that there are with Mercury. The National Environmental Institute in Suriname asked us in the university to find out what are now the levels of mercury in the natural soils that you find everywhere in the area where also gold is being mined. And the idea, of course, is that if you want to know whether a certain material is polluted or not, you must have a background value. So you know that because here in the Netherlands also, and everywhere in the world, we are speaking about background values of specific materials, metals, and so on. And that's also what they try to do in Suriname. And it is complicated because in principle, if you have a way to distinguish between polluted and non-polluted material, pristine material, then you have also a legal way of saying you are doing the wrong thing and so on. So that's the main point. So I will speak a little bit more on why this mercury is a point. We made a desk study first, and we have some field test laboratory analysis. We made a regional survey. We have compared our results with what we know about polluted materials, and that is more or less also the line of my talk, actually. So this is Suriname. It is formerly Dutch Guyana. For those who don't really know, it is a country which boasts itself that it has 93% of rainforest cover. It's the greenest country of the world. If you see what they do with the forest, I think there are some comments to be made about that. And the northeastern part is the so-called greenstone belt. And the greenstone belt is the area where specific rocks occur which can contain gold. I'm a bit have a bit of cough, so from time to time I will walk and take a sip of water.
One left.
Yeah.
Diana's in between.
Real water, no rum. So what you see on the map, actually, that is this is the greenstone belt. So it's no longer. Is it working? I don't see the pointer anymore.
Yeah, we see. We can see.
Oh yeah. Oh, no, it's the cursor again. Doesn't matter. So here you see the areas given for exploration, that's in orange, and in brown the areas for mining. Of course, exploration means that you may have a look what is there, but you're not supposed to start mining. But The real thing, of course, is that they are starting all over, that they are having mining all over the place. This is a nature reserve. The other part of the country has no greenstone formations, and in fact, there is no gold. It continues into French Guyana and also in Guyana across the Quarantine River. So when I was working in Suriname, this was my first job from 1972 to 78. We made a geological map of the country. So we have collected about 100,000 rock samples over a surface of 100,000 kilometers. So one sample per square kilometer in tropical rainforest. At that time, that was really something very special because at that amount of detail was not available in other areas. This is a digitized version which was made in 2018, and you see here. Okay, yeah, there we are. This is the area where we have been studying the mercury content. Not everywhere because there are very few roads. Few roads there are, but most of the transport into the gold areas goes along the rivers and so on. These are the different rock formations that you find in the greenstone belt. I won't go into too much detail, but it's good to understand that all the green ones here are volcanic rocks with most mafic minerals, so olivine or pyroxenes or amphiboles and so on. The red one is a granite. These are gneisses, and so these are sedimentary formations. This is another granite. This is sedimentary again. Those are some slightly younger granites. You will need those formations because we will see that they have a meaning also for the mercury content of the rocks that are there. So what happens? What is being done there? There are small-scale miners who sometimes legally, sometimes illegally, sometimes working for a big boss in the town who is in the parliament. Although they always say that they have no interest there. They have a power hose and they suck. They put a lot of with hydraulic power. They loosen the lower part of the soil profile because that's usually where the coarsest material is, and that is where the gold is being found. The gold has a specific density of 19. Quartz has 2.56. So you understand that by the density sorting in a river or also colluvial processes, most of the gold is to be found in the coarsest materials. So this is standard grade. But they have to get rid of everything. What they then do is they made a kind of slurry with all the water that comes out of the hose, and the slurry is being pumped to a place which is called the sluice box. And here, the sluice box, it has a kind of riffles, and all the slurry comes along the riffles, and the heaviest particles, the gold particles, they are being held by the riffles, and the final are washed away. But what they do now is they put a little bit of mercury on those riffles. Why? Because then you can get an amalgam, a mixture of gold and mercury, and of course mercury is very toxic. So you get this mixture of gold and mercury. You must get rid of it again. So these are the tailings. That is what remains. If you look what they are doing then, after that, well, this one too much. This one. Yeah, this gives just an example. This is where they are putting a lot of water on the lower horizons, and so it says addition of mercury to the lower. I've never seen that, and so, but it is a very complete picture. And so here you see that the slurry is being transported to the sluice box, and in the sluice box there is an addition of mercury to get the finer gold particles in the amalgam, and then after all. They have to get rid of the mercury and to get the pure gold. And if they do it rightly, then they have a distillation apparatus to pick up the mercury to use it again. But usually it's too much of a bother, and they just heat it, and the mercury vapors go all around in nature. And so that's the biggest problem actually that you can find there. So. That is one of the causes that there is a lot of mercury pollution there. So mercury, it is forbidden to import it in Suriname, and somehow it always comes here. So what we wanted to do, as I told you, we wanted to understand what is the natural amount of mercury in soil profiles. And here on the map, you see we have made two soil profiles at this place here. Afobakka, this is a road to the Afobakka storage lake further south and so. And a little bit to the west of it, there is this ferrosome that has been taken, I think, in the 70s. When has been, do you know when it has been taken? Liza? Liza, yeah. Do you know when it has been taken? No, no. Maybe it should. Well, anyway, so this profile is more or less representative. And one other detail. When I just started to work when I was a student, I was a student assistant with Herman Muscher. Some of you may know his name. He's working in Amsterdam. He was working, he died since then, but he was a great micromorphologist. He did a lot of soil micromorphology, especially Lus. His PhD thesis was of Lus. But he worked together with Wageningen, with Jongerius, and other people who were working here. Maya Koistra, she was more or less a successor of him. And at that time, because I was his student assistant, I was also working with soil micromorphology. And Herman Muscher came to visit us in Suriname in 1973. And from almost the same area, he took samples. So this is the micromorphology of a similar soil from the city. There are about 6 I've taken along all the time in my career, and now I have decided that I can better give them to the Soil Museum because I have no more work for it. I never did anything with them, and Herman also not. But I think it's a nice illustration of material. It was from 1973. So there are about 6 different slides, which have been in sections, which have been made from impregnated soil. You know these techniques, I suppose. Yeah? So, okay, what we did and so is we first wanted to try out how do I have to do this to determine the amount of mercury in the soil, because we had never done it. Nobody had ever done it so far. So it was a little bit experimental. So a few years before, I had found a profile along on the place where that I just show you, that Afa or this or that. And you see, this is a volcanic plastic material with a nice anticlinal structure in it. It was just clean because they was taking away here material for road construction, and so we just did the rainforest on top of it. So that is what I remember too. We went there, and then the next. Actually, this is the place then where we started to work to get an idea of, because we wanted to clean the surface along a road with primeval rainforest on top of it. This is just a typical laterite profile, as we call it. Maybe you call it different now. I haven't followed all the changes. I was brought up with soil taxonomy after 1975 and so on, but everything is found now.
Well, we call
So
it
what happens? So
Yeah.
in such a tropical soil profile, all soluble materials, calcium, magnesium, potassium, sodium, they are leached out, and you get a concentration of elements that are not leached so easily: iron, aluminum, silica, and so on. So that is, and you see the bedrock, saprock, which is still some characteristics of the bedrock, the saprolite, which still has some structures. So what you saw in the previous one, you see the typical saprolite structures because it still has some layering there. And then if you go further up, you go in the soil, you don't see anything more, and you get some colluvial layers or lateritic unicrust. Sometimes there is, sometimes nothing. So this was the picture I gave my students, because we have been with the 4 students, Suriname students from the Com University, and I told them to make several, in principle, 3 different samples. And this is not the normal way in which you would describe a soil. We haven't been looking at grain size, at pH, and CAC, and so on, because, well, first there was no time, and the second place we had a different objective, of course. But of course, it can still be done if you want to do, because I said just clean it and so make sure that it is that there is no dust from the road on it, and so and take samples 500 grams from at least 3 different places in the profile. Make sure you have the topsoil and you have the lower one. So this was the instructions that they got to go in the field. The samples that we collected were analyzed by cold vapor, atomic absorption spectroscopy. That is a laboratory field in Suriname who does a lot of analysis, mainly for the gold industry. They do fire assay to find the amount of gold, but they also have this and can do 40 different elements as well. They have quite a good laboratory, which has also its certifications by several institutions. So there we started, and we had two profiles at the same place. This is the same place, but you see, since from 2017 to 2021, it had degraded a bit, but there's no problem. You see still here the same structures that you saw on the previous slide, but here you see it is mainly soil. There's not much left from the original structures. Come on. Not much less from the original structure. So here we started sampling with these two profiles. And this is the first profile, and you see what is typical, which is lacking here actually. If you go deep enough, then you see it becomes reduced. It can get a reduced signature. It is being we call it a pellet zone, because it has been under the groundwater influence through. In the past, of course, not now, but in the past, it must have been leached by the groundwater. And so here we took 6 samples, and here also this is the other part that you see we took 6 samples, and these are the results that you see from the mercury. The first results we got from the fill-up. And you see 62, that is just to test the difference with this Edelman, or just with one from the wall. 51, 50, 55, 49, 59, 1. So you see an enormous decrease of mercury within the profile. And the second profile was a bit different, because you see 43, but that's 162. And the 162, that was an indurated horizon in the saprolite, and then it goes down again, 40, 18, 19, and so on. So what is known from the literature is that mercury is very much associated with iron oxide. Right? It remains together with the iron oxide. So what you would see here is actually a kind of residual enrichment. Actually, apparently, mercury does the same as iron, aluminum, and silica, because it is not leached away apart from the pellet zone. But it is being concentrated by residual enrichment in the topsoils. But we wanted to have a test. Is this correct? So we have those samples were also analyzed geochemically on 40 different elements. Not all the elements gave values above the detection limit, but the most important ones we have got. So here's mercury, aluminum, iron, chromium, vanadium, cadmium, niobium, lead, strontium, zirconium. All those elements apparently are also concentrated by residual enrichment in the topsoil. And that says listen, this is not just the first thing you might think is, yeah, well, this is the high amount of mercury in the top. That is just a result of atmospheric deposition or whatever it could be. But you see, it follows exactly the same curves as all the other elements, which are concentrated by residual enrichment. So that gives us the idea it is really being enriched just as all the other elements that we see here. This is the second profile. And you see it's different because here again you see that because of those hardened profile, the hardened iron oxide, you see changes also in aluminum and in cadmium, niobium, and so it is different. But the idea is the same. You see again that the lowest values are at the bottom of the profile. And so we here also believe that this is we have a good idea about that this residual enrichment is taking place. We had a second test area, and that was in the Nassau Mountains, near the Marowijne River. This is Marowijne River here, and this is the Nassau Mountains. They are bauxite plateaus. We will come back to that in a later in this question. But here there was a gold company who was working in this area in Wittlager place. And it's one of the areas that has been already since the 19th century prospected for gold. And we got one soil profile from 24 meters deep from a boring from a company in 1979. No, big view. It's a bit sensitive. And we see the soil, and we see the pellet zone here, the saprolite and the saprock. And saprock is greenish again, so it means we are very close to the original rock. So, but I don't see. Yeah, it's a picture which you can. Almost it's a mix up. So you would say this is a. This is also, it is not, the iron in the minerals is not yet oxidized yet. From here the oxidation of the iron 2+, the ferro iron is going to be, is still present, and here it's all oxidized. So, yes. Okay, everything, yeah. So here we have it, and it is a kind of andesite. And here we see the same thing, but over 24 meters. So mercury, iron, chromium, vanadium, only magnesium is also there, but magnesium has nothing. Magnesium is one of the elements that is leached and so, and you see there's nothing at all. But in the lowermost horizon, we find that there is still some magnesium. So that is the part that is not yet reached by tropical weathering. And we have also looked at the mineralogy. You see chloride. Chloride is a Fe2+ silicate. So that indicates that this part has not yet been reached by tropical weathering. It's the same part. It's a kind of andesite, so volcanic rock, which is. So you see the second site gives actually the same kind, on a different scale, the same kind of information as the first part. No, the third site is near Brownsberg. Brownsberg is a very famous plot area. Most people go there. It's a 500-meter bauxite plateau. It's a nature reserve, but in spite of being a nature reserve, there's a lot of gold mining around going on, and so they shouldn't do that, but apparently some crook official has given permission to do that. So it is at the bottom of the laterite plateau, but it is what you see there is a sloped duricrust consisting of colluvial material. This is the colluvial material with quartz, but also laterite fragments and so. And if we look here at the mercury, we see. It's so quick. We see that there is actually no regular order because apparently it is mixed material which has laterite and has quartz and so. So here we haven't made any multi-element analysis here because it didn't make sense because of the type of material. Now the next phase is that we went with a team of students and along all the roads in the neighborhood of Paramaribo, the capital, we did the same along a great number of soil profiles. This is the feral soil that is here. Also there we have sampled 62 soil profiles, 196 samples, and they all have been analyzed on both mercury and a few of them also on other metals, but mostly only mercury because we had an idea that we had already the idea that it was the result of residual enrichment. And so this is just 2 pages from students' reports where they said what they have Munsell color indicated sometimes. That's what they did, and so and what kind of minerals they saw. But for the rest, is not much information that you would like to have as a soil scientist. But anyway, that is the way we had to work to do this kind of analysis. And apparently nobody had done this before because what I see is that they really wanted to have our paper at the Science of Total Environment because, well, it is what you can do if you are partly soil scientist, partly geologist, and so on. So here you have the different rock types that we have sampled, because we know the underlying rock types of the geological map. You will see that in the so you see here that there are quite a lot of differences in the top, what's in the top and what's in the bottom. And so on average, what you see there's one is 807, and in the Goliath Mountains, and so there are quite a lot of differences. And I'm not going to explain that for all the different rock types, but I have made a little graph which shows that there are differences between rocks that contain much iron and magnesium and rocks which have mainly quartz and feldspar. This is granite, gneiss, sediment, and so on. Storage systems are very rich in iron, volcanic rocks as well. So you see that it depends, the amount of mercury that is concentrated depends on the type of underlying rock. So iron, magnesium rich rock, that is volcanic storage system, that are the most typical. So again, we see apparently the amount of iron that's present in the soil, in the rocks, at least partly determine the extent to which the mercury is concentrated. And we made a map. This is the geological map of the same area, and if you see the highest values of only the highest values of the profile, they are mainly in the green areas, that are the areas which have volcanic rocks below, and the lower ones with the blue, and so they are mainly in the sediments. It's not always precise because this map has been made in the 50s, and when there were not many outcrops at that moment, so there are some inconsistencies, and there are all sorts of problems with sampling from the stream. But the reddish spots are usually in the Paramaca volcanics, what you see. This is all sedimentary, and this is the storyline garniches, which is here. So there is a very clear relation between the underlying rock type and the amount of mercury in the profiles. Of course, you want to know how much mercury is in the rock itself, because so we have been able to get geochemical data from one of the mining companies who is working here, and they have all hard rock cores, diamond drill cores from 10 different formations in the area. And we have looked at their key geochemical tables, and they say that out of 113 samples, only 35 have original in the rocks itself mercury content of maximum 40. The rest is all very low. So that means that it is not the amount of mercury that is present in the rock, but it is the soil forming processes that make that the mercury is concentrated by by tropical weather. The Canadian gold mine, Roosevelt gold mine, that has been sold to Chinese people recently. Well, if you look, the bauxite industry is also mining bauxite and converting it into aluminum oxide to make aluminum. There was very big bauxite industry in Suriname, and so what they found is there's a lot of mercury in bauxite. There was so much mercury because it's the same process. It is tropical weathering, residual enrichment. There's so much mercury in bauxite that they every year, and they could find up to 13 kilograms of mercury from the vapors that came from by the production of the aluminum oxide. So that means I have asked one of those geologists who's working there. This is 2005. They started to capture those vapors in somewhere in the 80s, but they are already much earlier. So I suppose that before they captured the mercury, it was just blown by the trade winds all over the country. Now, I do not know what they do with this mercury, because this is more mercury metal. Well, this is Hg0. Maybe they sold it to abroad, they said, but of course it's very well possible that it is that of course it found its way to the people who are working using the mercury for their for small scale gold mining. Now these are different bauxites here. This is bauxites from the coastal area. These two are also bauxites from the coastal area, and this is the only one from the interior, which has up to 2,000 ppb. We always speak about ppb, so it's parts per billion. You can say nanograms per gram and so, but and you get real unwieldy numbers, and so we always speak about ppb here. So you see, also in the interior, they are much higher than elsewhere. If you come in here, you see a big chunk of Surinamese bauxite. If anybody tried to find out how much mercury there is there, I think it would be interesting because
tomorrow it's gone.
Huh?
Tomorrow it's going to be gone. Somebody took it.
No, but it's such a big chunk. It will not be gone, but so give it a try. It is not on hard rock. It does bauxite. This is on sediment, so I expect that it is rather on the lower side. Hugo is not here where it comes from, and so. But really, the Kaimangrassi Kurmotibo, we are also not so far from Mongo. Somewhere in this range you will find it. So I'm sure you will find some bauxite there. I spoke about the Nassau Mountains earlier, where we had drill core up to 24 meters. Nassau Mountains is a bauxite plateau, which to some extent also has been considered for bauxite bauxite mining. It has never occurred. Sorry. Could have stayed home, but I think I won't let it out. And but in the same area, they were also looking for gold. So the bauxite is still there, but they have been drilling quite a lot through the bauxite cap D. This one, here you see D. This is the same bauxite plateau. They have been drilling it, and here you see every point. The red point gives more than 2,000 ppb, more than 2,000 ppb. Remember, that's much more than we all found in the normal soils. So that is because of the concentration in the bauxite. In one place they found 11,000 ppb. So that's the highest number I have found in the geochemical data of this mining company, Suriname, exploration company. So it means this is another illustration that a lot of mercury is concentrated by tropical weather in the topsoil and in the bauxite itself. And this is still nicer because this is the story of a man in 1912 who was looking for gold in the same area, in the Nassau Mountains area, and so. And he was using mercury to get his to get the gold out of his prospect, and so. But to his astonishment, when he wanted to retrieve the mercury, it was the nice thing to do, of course, he found more mercury than he had put in it. So that was very strange. And so, and then he was looking around, and he saw that in the river gravel there are all these little red chunks or so. And this is cinnabar. This is mercury sulfide. This is samples. This is in Naturalis in Leiden. There's a lot of that material still available. This is gold, but the rest is all. So there's a natural mercury deposit there in the gold area. And you almost would say, is that what nature tells us? Here you have the mercury to get your gold out. Of course, it's a coincidence, and they are the same hydrothermal processes that produce the gold veins and of course the mercury. But it was discovered in 1913, described for the first time. So very heavy. So Billiton has been looking there. So far, everybody says it's not enough to make any to make a mercury mine there, but it's 86% of mercury. That's something different than what we have seen so far. So, okay. So, but what about the polluted material? How are the concentrations of mercury there? This is an older paper, 2002. And he says mine waste has 55, 5.5 to 200 ppb. Sediments in the stream below 110, 150. Uncontaminated baselines worldwide, 40 to 80 ppb. And he says also there's a correlation with mercury in the Roosevelt rocks in the mine where they were mining, and the methyl. This is of course methyl. That is the methylated variants of mercury, which is the toxic one, which is Suriname is a member of the Minamata Convention, and so they must make sure that the mercury is not being contaminating the people, and so they have been doing fish analysis, hair of pregnant women, and a big project is going on there, and the results are not completely convincing. But this methyl, mercury, which is formed usually under reducing conditions. So if you leave a hole with water, then the mercury, which is as mercury 2+, is solidly bound to iron, but when it becomes reduced, and iron also reduced, it is in a stagnant water that will be reduced, and then you get this methyl mercury, and that is being uptaken by water plants and eaten by fishes, and the fishes are being eaten by bigger fishes. The highest mercury contents are in the biggest fishes. They know that. There's a lot of research on being done in Suriname. This is another of the people from Altera, some Wageningen here, has been working also to find out. This is the nature reserve I was speaking about, the Brausberg, and this is how they are working here. All those people, they are living in small tents here. They move them anytime from one place to another, but you see the great disaster. This is supposed to be a nature reserve. So, but they have also done a lot of work, not exactly on this place, but it is Delta. It's on the other side of the mountain. Average soil primary forest, 200 ppb. Average soil secondary, 200. Average between pits, 200. Average sediment sluice box, 780. The sluice box, there are the conceptions with the riffles and so on. So that's higher. Average sediment in the pits, 250. Average sediment in the entrance to 300. Sediment and the exit of it, 300. It's the same order of magnitude of what you find in the pristine material. So that is a problem, of course. Right? And there's another way of looking at it. They have been looking at how much mercury is there in the river sediments. There has been a large study of rivers. And you see, also, I filled in here the PPBs. The colors are for the rivers. That has nothing to do with concentrations. But you see 250, 355, 53, it's 200, and so on. And the strange thing is, even in rivers where there's no gold, you find sometimes here as well, the Copenhagen, you find also mercury. So this mercury in the river cannot be the result of mining. It should have been deposited in atmospheric, maybe from the bauxite factories. And they also found these are profiles from the top to the bottom, that they found that the amount of mercury is increasing from the bottom to the top. Also in the Copenhagen River, this is the blue one here, where there's no mining at all. So apparently there's also a contribution of atmospheric deposition of mercury throughout the whole rainforest and so on. And another factor is not only bauxite, but in Paramaribo, in the capital, they have found that there are many small, mostly Chinese gold shops where they melt the gold to get the last mercury out. And so you get mercury vapors all over the town. They have measured that recently. So, and of course, the northeastern trade wind also blow this into the interior of the country. So it is not easy, and that's actually the quintessence of my story, that it is not easy. We have been able to publish this in the Science of Total Environment with all the names of the students. I would like to attract them to science by at least have their name published in 2022. You have a copy of it, isn't it, Thijs? So I can send it to everybody who will want it. So what else can you do? Mercury has 7 isotopes, and the isotopes behave themselves differently. You see here the red crosses. This is soils. This is rainfall data. This is the odd numbers, and these are the even numbers from the isotopes. Usually, the even numbers, they are related to mass-dependent fractionation. You know, of course, the whole system of when you have the ocean water is evaporation, and O16 goes a little bit more quickly in vapor form than O18. That is mass-dependent. Mass-dependent fractionation. It usually happens with the even ones. If I understand it well, it's not my field at all. And the odd numbers usually have mass independent, especially photonic processes have this type of handling mercury isotopes. What do you see here? Rainfall, soils. Here are the soils here in pink. It more or less in the middle, and so foliage or leaves are more in this side. You see some clusters, but they're quite overlapping, but still there are some clusters. Lichens here. These are geological materials, rocks, ores, mercury ores like the one that you see, coals, fine-grained sediments, marine sediments, freshwater sediments, marine sediments, and so on, anthropogenic or not anthropogenic. You see, there's a whole range as well. So we hope, but that is being done by others, that maybe if you find a way to find the right isotopes to distinguish the polluted material from the unpolluted one, that you can get a step further. But so far, well, there has been a few studies. I will speak about it. Anyway, of course, you would like more information about clay, organic matter, test profiles, the mercury isotopes, relation to mineralogy, and so on, redox conditions, and anoxic groundwater. That's what you want to study to find out what happens and so on. Our samples from the test areas, they have been sent to France, to the University of Toulouse, by a French geologist who was interested, and he's going to look at what he can find from different the different isotopes in that material. But I haven't had the results. It's rather recent, last year that he visited Suriname. A lot of work is being done. This is from a Surinamese PhD student, Lionel Vreetsam. Studies fishes and also looks where are in the fish are the isotopes, and the sources are complex. He says geological weathering, historical mining, current mining, gold processing, atmospheric deposition. It is not so easy so far. So we have not been able to give a spick and span procedure for the government to distinguish them. I think it's a negative result, but still we have understand a lot more what we didn't know before. There's a UNESCO ICGCP project, impacts on small-scale mining in the Amazon. I haven't seen any new results from it. I'm not going to. I was in Toronto last week and I forgot to go to this lady, although I was there for the mining conference. So after all, these are the conclusions, more or less. The primary hard rock, low values, less than 12 ppb. Topsoils iron cementerizer, residually concentrate mercury up to 100 to 200. Extreme residuals are in bauxite up to 1200 ppb, 12,000 ppb, that's the highest value we found. Deeper horizon, multiple pellet zones are depleted, probably by fossil groundwater, when the profile was still on the groundwater, less than 1 ppb, the same profile. So the range of values within individual profiles is higher than between profiles. Higher risk parent rocks and higher mercury. Higher risk is still one big problem. Higher mercury in topsoils than otherwise. It has its own will. I have no objections to own will, but sometimes I still want to control it. So the implications are unpolluted topsoils have mercury values in the same range as stream sediments and mine tailings. So the method is the mouse. I have trouble with mice, and so it's maybe because I have to catch at home. So this method is unsuitable to distinguish polluted samples from pristine, and probably isotopes is necessary. Mercury in soil is probably not a hazard as long as it remains bound to iron oxide in oxidized environment. Conversion to methyl mercury requires reducing conditions in groundwater and mine pits. So avoid stagnant water in gold mining areas. No, so at last, these are two interesting books for who is interested in gold and mercury in Suriname by a Delft colleague. This is my own book on the geology of the Guyana Shield, which is being published next month. So, time for you, questions?
Thank you very much. Salomon. Are there any questions from the audience?
No, you won't.
I'm not with you, just to see all this.
But this, you mentioned small scale mining. They used they vaporized the mercury to get it separate from the gold. But do you have any idea what the reach is of that vapor? Is it possible it's very local, or do you think it is? You should go down by yourself. You see which
No, what we see, what we think that is happening. It's difficult to quantify because they are small scale mining.
Okay.
But we think when you see how much gold is being produced, there will we measure in troy ounces, so 40-50,000, mainly made of this metal. The amount of mercury that was released is considerable. I shall have a look. I have a book on this by the National Environmental Survey. They must have the figures about it, but I think it is considerable because they rather go on mining than caring about for them it's more profitable to just go on mining. One of the things which I always try to find out is they have no idea of the geology where they are working. They only know the gold is at the bottom. So try to find out the geomorphic processes that have formed this material at the bottom of the profiles and so. There's absolutely nothing done so far. We know a lot about the gold in the solid rock, but very little about the processes that's concentrated, because they are not only in the river, but also on the slopes, and probably related to climate change, because during the ice ages, there was a savanna type climate, much more erosion, much less vegetation, like we here have in the Netherlands as well. We suppose that Pleistocene ice ages played a role also in concentrating the materials along the slopes.
Yeah, thank you, Rob, for this really inspiring talk. And I can also notice that you are still a good talker, since the 80s when I was following your colleagues. But I was wondering, is there any study done in terms of human toxicity and human?
Oh yes, very much.
If people touch these soils, to what extent they might get sick or have negative health impact?
Well, how how do the people get toxic amounts of mercury by eating fish? And that's always
That's
the
the
problem.
pathway.
And fish are not restricted to the mining areas. They go upstream, even beyond the mining areas. So even if you don't live in a mining area, then still you can eat fish and with mercury. And the biggest was what you call the Ayomara, Hopias. Those are the ones because the smallest fish start to eat the water plants, and so and the bigger fish start to eat the small fishes, and so you get a concentration. And there is a project which has made a statistical study of human hair, of birth outcomes, of also stress of women, and so they combined into my in my view, not in the best way, that they have both the chemical and psychological in one statistic thing, so that you never know whether it is the chemistry or say the psychological stress. But there are a lot of data available, but it is still, what I see, difficult to pinpoint. Well, now we have found the impact of the mercury in the medical data so far. They say, well, sometimes they say, yeah, we cannot find it because they have also selenium, and selenium is counter-effecting the idea of mercury. And so there's a lot of the 10 Surinamese PhD students are working on this specific project.
So it's mainly through bioaccumulation in the food chain, and not directly by touching the soil or by touching.
No, not so much. No, it is through the food chain indeed. Yeah.
Kind of two questions. So one is related to this. So do people have specific kind of guidelines? So regarding like what they can eat or not in Suriname, like practically?
Well, I am not sure. The poor people, they are obliged, more or less, to eat the fish. But some of them, they make their own fish cultivation ponds to get fresh fish and so. But not everybody can do that and so. But it is one of the things that they trying to get rid of the. But of course, they are poor people. They're living from very low conditions, and so they must get a certain amount of mercury. But the problem is not that we know that they have got it, and you can find it in their hair, and especially, and so. But to pinpoint that you have, if you have so much mercury in your hair, we see that your health is being impaired. That is difficult to say. So the Minamata Convention started, of course, in the same way in Japan, when they found out that people were eating fish with a lot of mercury, but here it's more difficult. I remember a different story from Bogota, from Colombia, where I also worked in the past. There's a certain area where you have black soils with extremely high amount of selenium, and the people knew that there was selenium, and they could see it because there were chicken without feathers, there were cows without horns, and so on. Babies with long hair, and so the toxic effects were known at that time. But the people who grew crops there, they must live, and they sold it on the market in the big town in Bogota, and they bought their own food from the market from people from other areas to make sure that they didn't get it. But of course, yeah. And so there are other ways in which you can try to avoid. I haven't done much research because, as I told you, for me this is a sideline, but it was so interesting, and that I think it is worthwhile to tell you here the story because this is where it belongs.
Thanks, Salomon.